So the chain rule basically tells us how we differentiate a composition of functions. So here it is, sort of the general statement. What will be most useful to us immediately is this general power rule that we're going to get to really quickly. But the chain rule just says, suppose y equals f of u is a differentiable function of u, and u equals g of x is a differentiable function of x. Then I could take their composition. Y is f of g of x. So g of x returns u values, and u values I can plug into f, right? So like this makes sense that this could be a function. And it just says if I want dy dx, right, y is a function of u. So normally I would be like, oh, I define dy du, right? But if I want to find dy dx, I could simply take dy du and multiply it by du dx. U is a function of x, so I can multiply that. And in a weird way, it's like, oh, these derivatives, I just think of them as a fraction, and those du's cancel. It's kind of weird, but the way that we're going to experience this chain rule initially, and we'll see it come up when we do like trig functions and log functions too, but initially for us, we're going to see it in the context of using the power rule. And so we're going to generalize that power rule. Right now, our power rule says, I'll do this in the margins here, that the derivative with respect to x of x to the n, what does this give us? How does the power rule go?
X to the n minus 1.
Just x to a power, right? In fact, we derived that rule ourselves. We used Pascal's triangle. We saw why that should be the derivative. So that's if I'm raising x to a power. Now what we're going to do is say, look, what if I'm not just raising x to a power, but I'm raising some stuff to a power, like parentheses, right? Some stuff that's a function of x that I'm raising to some power. What the general power rule says is that I can still use that rule, right? That nx to the n minus 1, like I can use the power rule on this, bring the n down, n times u to the n minus 1. I just have to remember to follow up by multiplying by the derivative of the stuff inside. So that's basically what this is. This is the chain rule. That times du dx is where we apply the chain rule. Applying the chain rule is what allows us to use that power rule, that super convenient power rule, on stuff that isn't just of the form x to the n. So as an initial example, we're going to find the derivative of this function, y equals 3 minus 5x squared, parentheses, all to the 7th power. What the chain rule allows us to do, this general power rule, says, okay, I'm going to think of this as stuff to a power. And I'm going to do this, I think, in two different ways, okay? In one way, I'm going to identify u, what u is in this function. So looking at the general power rule and the function that we have, what is u equal to?
3 minus 5x squared.
Yeah, it's the stuff that's being raised to the power. And I'm going to find du dx. What is that?
Negative 10x.
Right. So now if u is equal to 3 minus 5x squared, then what we have here, our function I could rewrite as y equals u to the 7th. And I could certainly find dy du. What is that equal to? 7u to the 6th. Right, I'm just thinking of this as a function of u. So what the chain rule says, and here I'm going to use this version of the chain rule the general version of the chain rule up here, theorem 4, right? The chain rule says that dy dx is equal to dy du times du dx. Now dy du is 7 times u to the 6. Du dx is negative 10x. Now I know what u is, right? We made that choice up here. I'm going to just plug that back in. And then we could simplify. So I have a minus 70x. here's the implementation of the chain rule where we're kind of explicitly identifying our u and our x. We're writing out what the chain rule says in the general sense and how I can make that substitute back in. There's sort of a faster way, like after you do a bunch of these, and I'm just going to show you right now, and hopefully it'll be something that we find convenient to use. There's a bit of a faster way to think about this. So rather than identify the u explicitly, here's my function as they gave it to us. What I need to do is recognize first that I do have stuff to a power, that it's parentheses to a power, and so this is something that the general power rule will apply to. And then I use that general power rule. I use it on the parentheses. So the general power rule says I just bring the 7 down. So let's see, I'm going to start right off with dy dx, right? I'm not doing dy du or anything. So the power rule would say, oh, I'll bring that 7 down in front. Then I rewrite the stuff in the parentheses as is. No changes at all. 3 minus 5x squared to the 6th power. This is like me just trying to bootstrap the power rule to this function that isn't exactly written in a form that was friendly to the power rule at first. But the chain rule says, oh, no problem. Go ahead and do it. Just follow through by multiplying by the derivative of this stuff here. So the derivative of 3 minus 5x squared we already found is negative 10x. This times a negative 10x. This is the chain rule. This is us using the chain rule. And then we simplify. A little bit faster way to think about it. Not necessarily faster to hear me talk about it, because I'll, talk at length about anything. I mean, either way you want to approach it works.
Is the right side the chain rule? Because it looks like the general power rule.
Well, it is all the general power rule. The general power rule is what does the chain rule look like specifically when coupled with the power rule. So the chain rule says for any function, not necessarily an x to the n function or a u to the n function, I can find dy dx by multiplying dy du times du dx. And what it looks like when we apply it to a function that is of this form, parentheses to a power, we can go sort of work it out the longer way, where we're explicitly identifying all the things that appear in that theorem 4, for the chain rule. But in practice, at the end, there's sort of a lot of this middle work we can kind of cut out and just say, oh, I'm thinking about this just using the power rule. The general power rule is the chain rule, but just applied to u to the n, if that makes any sense. It'll make more sense when we get into like chapter 4, when we're starting to work with other types of functions.
How did you get y again on the left side?
Oh, the u to the 7th?
Yeah.
So when we looked at this function that they gave us, we said the stuff that's being raised to a power, that's going to be our u, right? So if 3 minus 5x squared is u, then 3 minus 5x squared to the 7th is u to the 7th. I just made the substitution.
Oh, okay.
Yep. Other questions?
So then your dy dx is a derivative of u, and your dy du is a derivative of y.
Well, dy du is the derivative of y. Du dx is a derivative with respect to x, yeah. Because when we write it out this way, what I'm trying to do is say, well, I know there's a bunch of stuff here, but I'm going to call it u, and then if I write it this way, dy du is easy because it's just the power rule, right?
Yeah.
And here, du dx is easy because it's just the power rule. And then the chain rule says I just need to multiply these together and then make my substitution back in. But we kind of roll all that into one step when we do this here. These are equivalent. These are the same. Doing this implies that we can do this.
Isn't it more, or if there's another variable that say it says find dy dx if k equals that's when you would have to substitute the u, and you wouldn't be able to do the right hand side.
Right. I mean, yeah. When we do implicit differentiation,
So
it'll feel a little bit more like this way to us, although it's
because
still the same rule.
Sometimes you have to use the u.
Yeah, like this here. Well, sometimes we have to use a u Well, most of the time we have to use the u in order to go backwards, and we're going to do a lot of that when we start integrating.
Yeah.
But, so this, in a way, like this step here is sort of like our crutch, or like our little, I don't want to say training wheels, because like this is still like pretty sophisticated, and in fact, this almost feels more complicated than this. But it is, I think, valuable to think about, okay, what is the stuff inside? And viewing that as a function in its own right, that 3 minus 5x squared. Because this really is a composition of functions. It's the 3 minus 5x squared function stuffed inside the u to the 7th function. So, yeah, okay. Are there questions on how we got this result using either technique before we go on to another one?
Just how did you know to stop there? Because can't you continue just a little bit further with like throwing that?
Oh boy. Yeah, so I know how to stop. I'll tell you how I know when to stop. It is absolutely delightful to get a result that's factored. If I look at that and I want to know where it's equal to 0, oh my gosh, easy. It's equal to 0 when x is 0, or when 3 minus 5x squared is 0. It's the only times. If I FOILed it out, first of all, I don't want to raise anything to the 6th power. I mean, I'd rather not, because it introduces an opportunity to make errors, and then it makes it so much harder to actually analyze. We're going to do some applications in the next chapter, which we'll get to probably sometime next week. But like right away, you're going to start seeing like, oh man, if I have this in a factored form, like I can do analysis and like find out a lot more about what my function's behavior is if it's in factored form. So I've got dy dx expressed only as a function of x, which is great. And it's in a nice factored form. Not to mention, sometimes we can't FOIL things out. I mean, that's a positive integer power, so we could, but what if that was something to like a 1/2 power? Can't do anything with that anyway. All right, so these problems are great. You're like, oh no, she had to say how great they are. That means we might not like them. But so as I've said many times, calculus is a course in which algebra really shines. So we have to be a little bit careful. There's definitely some algebra involved when we are finding the derivative of a function that involves either a product or quotient rule together with the chain rule. So first of all, how do I know this involves a product rule?
Something in parentheses to a power.
That's not a product rule.
Oh.
I mean, this is parentheses to a power, but there's no product rule
You
there.
have something that's multiplied to that.
Yeah, and they both have x's, right? I'm multiplying two things, both of them have x's. That's a product rule problem. But it also involves a chain rule because I've got parentheses to a power. Yeah. So let's identify our factors. So let's say our f function is 3x squared. Then what is f prime?
It's the
Yep. Right, we bring the 2 down, multiply it by the 3, and then decrease the power by 1. Our g function, the other factor, 2 plus x to the 4th to the 5th power. Who wants to have a go at, and not necessarily the final form, but like how we start, like how do we start this derivative? Yeah.
What would stop me from using the chain rule before the power, or sorry, the product rule? So
How do you mean?
Can I remove u and then start futzing around with the product rule using u as a template instead of?
So you're saying like if you let u equal 2 plus x to the 4th,
Yeah.
and then writing this as 3x squared times u to the 5th?
Yeah, and then using it as f and g of that.
I mean, then g would be u to the 5th, and you still want to find the derivative of g with respect to x first.
So we don't
So
have to use
if you wanted to use u equals 2 plus x to the 4th, you'd have to do that here in this side work.
But we don't have to use u.
Yeah, I mean, in a sense, we are automatically using u in the background.
So g prime is 5 parentheses 2 plus x 4 parentheses 4
Yes. So if you want to do the U thing, that's fine, but like then when you apply the product rule, you have to multiply, you're going to have to find G prime, and that G prime is with respect to X. I mean, I suppose you could leave it in U's at first, but you got to put those U's back in anyway. And yeah.
Where'd the 4x cubed come from, sorry?
Oh, good question.
Multiplying by the derivative of the
Oh, okay.
That's the chain rule right there. Yep, good. It's what allows us to use the power rule on parentheses to a power. I'm allowed to do it. I just have to follow through with the chain rule.
I'm still missing where that came from.
The 4x cubed? So first, and I know this is not specifically your question, but I'm going to start here. First we apply the power rule. So you bring the 5 down, and we have this stuff as is, no changes, to the 1 less power. There's our power rule. And the general power rule says I can go ahead and do that as long as I follow through by multiplying by the derivative of the stuff inside. And the derivative of 2 plus x to the 4th is 4x cubed, because the derivative of 2 is 0. And the derivative, and then we use the power rule on x to the 4th. So we could simplify g prime a little bit, 20x cubed times 2 plus x to the 4th, all to the 4th power. So here's our side work. Now, let's put this together. Gf prime plus fg prime. I'm going to just plug stuff in from the stuff we did over on the side. G times f prime is 2 plus x to the 4th to the 5th power times 6x plus f is 3x squared times g prime 20x cubed times 2 plus x to the 4th power. Now this expression right here is equal to r prime of x. It is very much unsimplified. Definitely not okay to leave it there. We still have, I would say, a decent chunk of the work ahead of us. But it's algebra, so we should be pretty excited about that, because we could do algebra all the livelong day. Okay, now here's what we're going to do. We're going to factor out the greatest common factor. And I want to think of this as I've got two things I'm adding together. I've got this chunk here and this chunk here. So when I'm comparing these two terms, right, that we're adding, what's the greatest common factor? What are things we can take out? What are some factors, common factors? An x, just an x to the first, right? Because it's always the least power. This has only got one factor of x.
2 plus x to the 4th.
Yeah. So I've got like this parentheses.
So you just have one left to the first.
But what's the power of 2 plus x to the 4th I can take out?
4.
Yeah, right? So I take the smaller one. And then there's one more factor. You're going to feel silly when I tell you what it is.
3.
6. But yeah. I mean, 3 times 20, there's definitely a factor of 6 there, right? So 6x times 2 plus x to the 4th, all to the 4th power. So we're going to take that out. Open up a set of brackets. So in this first term, I'm just going to start here. I took out the 6x, so I don't need that at all. Right? I grabbed that, so I just need a factor of 1 for that, which we're just probably not going to write. How about to get myself from parentheses to the 4th power to parentheses to the 5th power?
2 plus x to the 4th.
Yeah, just all that to the 1st power, which we usually don't write the 1st power. But this first term, 2 plus x to the 4th. And then we bring down our addition. Notice that if I took this expression and multiplied it by 2 plus x to the 4th, I would recover this expression, that first term. That's what we want.
So you just factored out of the left side of with a plus sign.
So far, and we're gonna keep going. What goes on the right side of the plus sign?
10x to the 4th.
10x to the 4th, that gets us to this, right? I took out the 10, I took out the 6, 3 times 20 is 60, so that means I still need a 10 to get myself to 60. And then I've got x to the 5th here, but I took out an x to the 1st, so we need an x to the 4th.
And that's it, right?
And that's it, because we took out the parentheses to the 4th power, right? That's all of it. So, like this, if I, like these first two factors here, if we multiplied them together, we get 60x to the 5th. So that's where the 10x to the 4th, I took out the 6x. So to get myself from 6x to 60x to the 5th, I need a 10, I need an x to the 4th, and that's there. I took out the 4th power, the parentheses to the 4th power entirely, so that's already taken care of. If I took this expression and distributed it to the second term, I would recover this expression. That's what we're trying to look for, right, when we're factoring.
Then we could just add that last x.
Yeah, we just combine like terms, simplify the stuff in the brackets. This is 11x to the 4th plus 2. And look at that. It's a beautiful, simplified expression. Figuring out where that's equal to 0 is really quite simple. In fact, I can tell you I'm going to do no algebra. This is 0. I mean, the only algebra I need to do, I can do mentally, all right? The only algebra, like, if I want to know where that's equal to 0, it's 0 when x is 0. That's it. Because 2 plus x to the 4th could not possibly be 0. X to the 4th is always non-negative. X to the 4th is always non-negative. That's never going to be 0. So this is 0 only when x is 0. Which means if I were to graph that function, and we're looking for like a peak or a valley, the only time it would happen, if it happens at all, is when x is 0. And I can tell that without plotting it, without graphing it at all, without plugging it in my calculator. Just by doing very enjoyable algebra. How's that? This kind of algebra, so this feels like a bunch of algebra. It is a bunch of algebra. Your feelings are valid. But this algebra that we encounter when we're taking the derivative of a function that involves a product rule or quotient rule together with the chain rule, like we see, it always is the same thing. Like, we're always going to be in a position where I can identify a greatest common factor. And notice that one thing I want us to notice is that because of the form that the product rule takes on, gf prime plus fg prime, like we're taking terms of which one we're taking the derivative of. So in one of these terms, one of these products, right, we have taken the derivative of the parentheses function, and one of the terms we have not. And that means that these powers will always differ by 1. And so when you factor out the greatest common factor, in one of these terms, you'll need those parentheses to the first power, and in the other one, you're not going to need it at all because you will have taken it out completely. So there's some patterns, right? Do all of the practice exercises. Like, just get used to it. Like, the algebra will always work out the same, so you really will get some familiarity as you work through these problems. Plus, the algebra is quite enjoyable. Now I've got some good news for you. Are you ready? Were you waiting for good news? More good news? This general power rule works even if our exponents aren't positive whole numbers, right? We've been really just focusing on polynomials and parentheses to some positive whole number. I mean, but it also works on fraction exponents. It also works on negative exponents. So if I'm given a function like this one here, I can write it first in a power rule friendly form. I mean, if you really just love taking the limit as h approaches 0, I'm not going to stop you. But it's a little bit easier if you say, I'm going to use some algebra. I'm going to be clever. I'm going to rewrite this as x squared plus 1 to the 1/2 power. Now it's parentheses to a power. The general power rule applies. And if I want dy dx, who wants to have a stab at how we would start this process?
1/2 times, what's the parentheses, to 1 minus
1/2 minus 1.
Actually,
Negative 1/2. Is that it?
no, then times 2x,
Yeah, where's the 2x come from?
derivative of inside the parentheses.
Mm-hmm. That's our chain rule. And then, simplify. The simplifying here is simpler to do. Right, the 2 and the 1/2 cancel. So I have x times x squared plus 1 to the negative 1/2. And you could leave it that way. I find it a little more desirable to go ahead and, first of all, note that they gave us the original function in a radical form. It's pretty common to give an answer adopting the same form. But also, I find it convenient to write it in that form. Let's see, if I go back to radical form, how would this look?
X over x squared plus
Mhm.
one.
Over,
Square root of x.
yeah. Yep. So let's just remember, let's take a minute and recall that for exponents, the fraction exponents, we use this fact right away, right? Fraction exponents denotes a radical. So a square root is a 1/2, a cube root is a 1/3 power. The negative power is what throws it in the bottom. The reason I find it convenient to use it in this form is I can easily, like, where's this equal to 0?
X is equal to 0.
Any other places? No. Look how easy that was. Low-hanging fruit right there. Mathematicians are lazy, all right? They work very hard to find the easiest way to do something. Questions on that example? Yeah.
So we get the negative 1/2 because we subtracted an entire power's worth.
Yeah, this comes from the 1/2 power minus 1. Yep. Other questions? Okay. There's more than one way we could approach this. I think they all start the same way. Anybody want to have a go at that? How might we, what's a helpful way to write this function?
Next one.
What's that?
That's the next one.
Uh-huh. So what exponent would that be? Yeah, the cube root is the 1/3, so we could say it's x squared, parentheses, to the 1/3 power. Now from here, you might say, oh, I've got parentheses to a power, so I can use the general power rule, and you're absolutely right, you can do that. We can also do a little bit more,
2/3.
yeah, we could just do a little more algebra first and say, oh, this means that y is equal to 4x to the 2/3, and I'll just use the power rule on that. Then I don't have to use the chain rule. There is no chain rule here, because it's just x to a power, right? It's not stuff to a power. Or another way to think of that, I don't want to say there's no chain rule. It feels like there's no chain rule. It's just that if I were to apply the chain rule and multiply by the derivative of x, what would I be multiplying by?
2x.
No, 1. The derivative of x is 1, right? So it's sort of like the chain, it's not that the chain rule only exists for stuff to a power, it's just that in simple cases like this, the chain rule would just have us multiply by 1, so we don't write it out. So how do we start with the derivative here?
So it would be like 8/3 x to the 1/3.
Mm-hmm. And that 8/3 comes from 4 times 2/3. X to the what power?
To the 1/3.
How do we get
I
1/3?
mean, no, negative 1/3.
Negative 1/3. Right, 2/3 minus 1 is negative 1/3. So I could write this as just 8/3 x to the negative 1/3, or I kind of like the way it looks if we just put it in a fraction and radical form. So we have 8/3 times the cube root of x. Where is this equal to 0?
When x equals 0.
Well, when x is 0, it's
Divided by
undefined.
0. Oh,
So Patrick said,
Nowhere.
why?
Because 0 and the numerator is 0.
Yeah, and guess what is true about 8?
It's never going to be 0.
It's never 0. 8 is not 0. Crazy fact of the day. It's sort of like 2 zeros put together, right? Like typographically, but not mathematically. 2 zeros put together mathematically turns out still 0. So, let's do another one. Couple ways we could view this function. 2 paths forward, yes?
We pull it up through the top and then 1 subtract 4x to the negative fifth.
1, say that again.
1 subtract 4x to the negative fifth.
Why subtract?
Because you pulled it through the bar.
Yeah, but it's not subtract, it's just times, right? So if 1 over something is just that to the negative power. So it's 1 minus 4x to the negative fifth. He said 1 minus, I think, right? Did you say minus or no?
You said minus 5. Right?
Oh,
Sorry, didn't
I
say
thought you said 1 minus, so
minus
anyway,
five.
my mistake. So we could write it in this power rule friendly form. There's another path forward. Anybody have another thought that came to mind when you looked at that? You could do like the quotient rule, right? The quotient rule is a little bit more work. I'm just pointing out that if that was your thought, it was not an incorrect thought. Often there might be more than one path forward as we're working with functions. It's a little bit easier to do it this way. And I can always tell if I can avoid the quotient rule or product rule if one of the things is a constant. Right? If there was an x on the top and the bottom, like I'm not going to avoid the quotient or power rule. But because there was a constant on top, then rewriting it this way avoids having to use that at all. If there were an x on top, then rewriting it that way just turns a quotient rule into a product rule, and I don't know that that's any less work. Let's find the derivative. Who wants to get us started?
-5.
-5
1 minus 4x in parentheses to the -6
to the -6. Yeah, we're subtracting 1
times -4.
times -4. And where does that -4 come from?
The derivative of the function.
Yeah. Yep, there's our chain rule. Questions on how we've started this? We still have some simplifying to do. So we get 20, positive 20 times 1 minus 4x to the -6. And I'm going to rewrite it in fraction form, in part because, well, where is this equal to 0? Nowhere. Because what's our favorite fact about 20? It's not 0. And it's a little bit more obvious when I write it this way that it's never 0. Sometimes if I write something as a product, I'm tempted to just set this product equal to 0 and think, oh, maybe I'll get a solution when this is 0. But of course, when that's 0, that actually just means we're divided by 0. Patrick's out. He's done. Questions on that example? Okay. All right. What makes this one different than the last one? We have x on the top. Yeah. We really just kind of need to use the quotient rule. It's possible to rewrite it so that you just have to use the product rule instead, but I don't think that's less work. So, yeah, we're not going to gain much. There's not like a power rule friendly form for this one because there's an x on top as well. So, our f function, with the quotient rule, f is always on top. And what's f prime? 1, yeah. Our g function, how do I want to write this?
First power, because it's the square root.
So what does the square root correspond to? So the square root itself corresponds to the positive 1/2. Sure, but with the quotient rule, we're finding the derivative with respect to x of f over g. Like g is as it appears in the bottom. So if we're using the quotient rule, then g is 1 minus 4x to the positive 1/2. The fact that it's in the denominator is baked into what the quotient rule is. Yep. All right, who wants to have a go at finding g prime? How do we start that?
One half to 1 minus 4x to the power of negative 1/2 times, what is 4?
Negative 4, yeah. And where does that negative 4 come from?
From the inside of the parentheses by u.
Right, yep. So there's our chain rule. The chain rule takes very specific derivative rules, and we're going to learn more as we examine different types of functions. You know, we're going to kind of stick with these algebraic functions for a while and do some applications with them. And then in chapter 4, we're going to branch out to other types of functions, like the trig functions, the log functions, the exponentials. Chapter 4 is great fun. So, but the chain rule is what takes these very specific functions and allows us to generalize it to like a whole family of functions. Right? It's not just sine x that we'll be able to take the derivative of later. It's sine of whatever, right, that will apply. So a chain rule is really a pretty powerful tool. So if I simplify g prime, we get negative 2 times 1 minus 4x to the negative 1/2. Now, here's our side work. dy dx. I'm just going to write out, how does the quotient rule go? Yep.
Times g plus g prime times f.
Over g squared. Oh, and there's a little mistake here.
Plus b minus.
Yeah, it's a minus. We subtract when we're doing the quotient rule. All right, let's start plugging stuff in. G times f prime. 1 minus 4x to the 1/2 times 1 minus g prime times f minus a negative 2 times 1 minus 4x to the negative 1/2 times f, so that's times x. And this is all over g squared. So far, so good. I'm going to clean this up just a little bit before we start the simplifying process. So I've got the 1/2 power, parentheses to the 1/2. This is going to end up being a plus 2x times 1 minus 4x to the negative 1/2 all over. And then the bottom, I guess I just have 1 minus 4x. We are going to summon all the energy and power that we have inside ourselves. And remember that you cannot cancel over addition. So don't do it. But what we can do, if we look at what we have up top, yeah, we're going to factor out the greatest common factor. And what is that greatest common factor in this case? To what power? Negative 1/2, always the least power. So you compare the exponents, whichever one's less. Take that. Now, what goes in the brackets?
2x.
So how do we get to this first term? Like, what do I multiply this stuff to the negative 1/2 power to get stuff to the 1/2 power? Positive 1/2 power. Nope. I'm going to ask you a related question. What do I do? Like, if I knew, well, if I knew what this exponent was, right? Forget about what's on the other side for a second. Suppose I knew what these exponents were. These bases are the same, right? How would I find the product? Add the exponents, yeah. So when I ask what's the power on x that I need to multiply by to get the 1/2 power, I'm basically asking, what do I need to add to negative 1/2 to get positive 1/2? 1, positive 1. And in fact, that always happens when you're doing this type of factoring that involve like the product or quotient rule with the parentheses to a power. Because of how those factors appear, in one instance I've got the derivative of g, and the other instance I don't. Those powers always differ by 1. So when you're doing that factoring, in one instance you're going to need that stuff to the positive 1 power, and in the other instance you won't need it at all. So what do we need in the first
1 minus 4x.
1 minus 4x, just to the first power? Yep. And then we bring down the minus, or sorry, the plus in this case. And what goes in the next spot? Plus 2x, because I took out the negative 1/2 power, and that is the negative 1/2 power that we have here. And so I've already got that, yeah.
Wait, so since it's always going to be the smaller
Uh-huh.
exponent, you always drop that endpoint. Or the, like,
Yeah, whichever one has it, whichever term has it. In one instance, when you do the factoring, like these exponents, you're guaranteed, because of how the product and quotient rules work, you're guaranteed that in these instances where it also involves that parentheses to a power, in one case you're going to have parentheses to you're guaranteed that these exponents will always differ by precisely 1. Because one of them I obtained by subtracting 1 from the power, right? So when you do the factoring, identify the least power, we're going to take that out, and then in one case you're going to need that stuff to the first power, and in the other term you're not going to need it at all, because you took it out exactly. We're going to simplify, of course. We got some like terms that we can combine in the brackets, but also, while I'm at it, maybe throw this downstairs, because that's a negative 1/2 power. So up top we have 1 minus 2x, after combining like terms. In the bottom, 1 minus 4x to the 1/2 times 1 minus 4x. And look, those are like bases, so we can add the exponents. So we get 1 minus 4x to the 3/2 power. There's dy dx. That's part of what they asked us to do. And then they said evaluate it when x is negative 2. So that's 5 on top. On the bottom, we have 1 plus 8 or 9 to the 3/2. And the 3/2 power of 9 means we're going to, the 2 in the bottom says take the square root. That gives us 3. And then the 3 up top in that exponent says cube that. So we'll get 27. So we get 5/27. Does this, if I were to look at a graph of the original function, right, that they gave us to start with. Would I notice any peaks or valleys in the graph? And if so, where? If I looked at a graph of the given function, the function they gave us, that x over the square root of 1 minus 4x, would we notice any peaks or valleys in the graph? Like any places where the graph might do something like this or this? And how would I tell? What's that? I mean, there might be lots of other behavior happening on the other side, but I just mean like locally, if I zoomed in, would there be any little spots where I might notice a little peak or a little valley?
X equals half.
Why a half?
Is it a zero numerator?
Yeah, like if I'm looking to detect peaks or valleys, that means I'm looking to detect places where the tangent slope is 0, right? Where the derivative is 0. So we have a nice simplified derivative here. And if I were interested in figuring out where's the 0, all I need to do is set the numerator equal to 0, right? A fraction's only 0 when the top is, and that happens when x is a half. And in fact, let's just see. So x over the square root of 1 minus 4x. And maybe I'll go from minus 5 to 5 on both axes at first. I might need to make an adjustment, but we'll see what this looks like. So what did we notice? We know that if a peak or a valley happens, it happens when the at x equals 1/2.
Why did it do that?
Why did it do that? So it looks like something weird happens right around here. And that even looks like it's probably before we get to -1/2 or +1/2, right? In fact, none of the graph seems to exist over here.
Is that the limit?
Well, sort of. To me, when I look at that, it looks like, oh, maybe there's a domain restriction. Yeah.
Anything under or over
Where would that domain restrict? Let's look at the original function. Where would that domain restriction come from?
Y-axis?
Right, but like, I mean, where specifically, like, if I look at how this function is written, what is it that I'm looking for when I consider domain of a function? What is the domain of a function? What?
input?
Yeah, like what is allowed, what we're allowed to plug in.
All real numbers, right?
So you're saying I could plug in anything I want to that function?
Other than 0, right?
Yes,
You're-
Pretty sure I can plug in 0, I'll get 0.
It's like acceptable input.
Yeah. What kind of inputs would throw an error? What do we look for? We look for dividing by 0, which sometimes results in a hole and sometimes results in crazy behavior. What else do we look for? So these are what we call real valued functions. Plug in real numbers, get out real numbers.
Oh, imaginary numbers.
Imaginary numbers. In fact, anything that makes 1 minus 4x negative, and in fact, because it's in the bottom, also 0, is not in the domain of this function.
So we can't.
So in fact,
we can't graph an imaginary number.
right. So any values from a quarter and on and bigger, 1/4 and bigger, aren't even in the domain. So if this function had a max or a min, it would happen at 1/2, right? But so what we're learning here partly is like, yes, we can use the derivative to detect maxima and minima, but what it does is it gives us candidates. If it has one, it'll happen at this or these values. And then it's up to us to kind of go a little bit further. And we're going to do that a whole lot like in the next chapter, but I'm just kind of trying to get us primed for